Good afternoon, everybody. Today, we're going to talk about problem number 2 of USACO 2023 January contest, the Platinum Lab. Here is problem number 2. Mana collection. The problem is you basically have n mana pools, and each one can accumulate n manas per second, right? And the pool are linked by a collection of directed edge from A to B, and you can travel from A to B by time of ti seconds. When Bessie the cow is at a pool, he can collect all the manas stored in that location and then empty it. Then he can go to another location, right? So then there's a bunch of curious you need to answer, means the total time is a second, and you need to end at the pool E, right, the end. And what's the maximum number of manas you can collect for S seconds, right? So in this case, for example, there's 2 pools, and there's one road. It's the first pool you can collect -1 per second. Second is 10, and there's a directed path from 1 to 2. And it takes 10 seconds to travel. So then there's 4 curves. Right. So now let's look at n. N is 1 to 18. What does that immediately tell you? Right? N is less equal 18. So now we clearly know, right? You can do it by O2 to the power of n, right? To that order. Okay, you can actually do n2 to the power n. Right? That immediately tell you is bitmask, right? Okay, that's the hint from that. Now let's look at the problem. You will end at the point E, right? Let's look at one query. You end at the point E. So let's say we have a path. Let's call this path P, okay? It go from P1, that's a path go to P2, and keep on going, right? To the last one, let's call it E, which is, let's call the length of the path is K. P is what's P of K. Okay, so let's look at the end point, and each one, right? You collect the mana increase by m of I per second, right? Okay, so for total of S seconds, and the travel time from here to here is T of I, right? So if you think about the point before the end, okay, and take, let's say, T of K minus 1 to travel this much. When you want to get here, obviously you want to get here at the last second, right? At the end, because if you get here early, you have to wait here for this to grow another additional one, right? At the end of S, then you collect it. So you want to reach this at time S. That means you want to stay here as long as possible, right? The last time you want to stay is S minus T K minus 1, right? So by the same thing, if you go backwards, let's call each time, it's the optimum time. okay, to stay at each point is S optimum at that time n, right? So then obviously the S is the S k minus 1 is S of k, which is S minus the shortest distance, right? The shortest distance in terms of time from the point k minus 1 to point of k, right? So S k minus 2, I mean optimum k minus 2 is S optimum k minus 1 minus the distance from k minus 2 to, I mean, p point of k minus 2 to point of k minus 1, right? So on and so forth, so on and so forth. So now, then let's define a dp, okay? Let's say for this pass, right? It's from 1 to 2. We don't know what exactly this pass is. So let's say for this pass, and it will reach the end, the point of u, right? What is the maximum mana I can collect? Okay. So it obviously is I have to travel through this pass, right? From 1 to k, right? I have to travel through this pass. And at each point, I collect a mile of mana for how many seconds? That take S optimum of I, right? Because this is the time you left, point I. So if I take this and put in there, so that equals, I'll put this way, of this sigma of M of I of S, the final S minus, you can sum up, right? All the distance in before. So it's from I all the way to, I mean, this is to point U, right? So let's say is, U minus 1 of distance from J to next one, right? So you basically, the optimum point, any of optimum point here is S, the final point, minus all the distance you traveled, right? Okay. So if I expand this a little bit, okay, if I expand this a little bit, so this is sigma M of I times S minus sigma I from 1 to U M of I times sigma J from 1 to U minus 1 distance P of J minus P of J to P of J plus 1, right? So see, this S is constant, right, for this PU. So let's put it like that. So I can take the S out. Okay. So what do you see here? If I make this, if I call this A of this pass P, right? This is independent of S, right? So if I call this is B of pass P, what we got? We got dP of P of U is A of pass P times S minus B of pass P. So what is this? This is a linear function, right? So if you take So if I do, this is my S, right? And this is my dp of p of u. For each pass, right, I may have something like this, right? My second pass could be, for example, something like that. My third one could be something like this, right? I want to find the maximum of this thing, right? So this immediately tell you, what is this? This is the convex Hall problem, right? So clearly, then let's go look at the convex Hall problem from Benjamin Chi's again and USACO guide, right? So this is in USACO guide, Platon level convex Hall trick. Right? So if you have bunch of linear equations and you want to find the maximum condition of that combinations. So what do? You use the convex Hall solution for that, right? This is a standard problem we have. Okay. So what's the question is, what's for people who are not familiar with it, I suggest you go back to this Benjamin Chi's USACO guide Platon level, right? Try to look at this and do some study on how the convex Hall problem works, right? So now let's look at the complexity. The complexity is we are trying to look at all the vectors, right? That is O of m factorial. Okay, O of m factorial is not something we want, right? So the question is, how do we get from m factorial to 2 to the power of n? Okay, so let's look at that. Let's look at the A of p and B of p. Okay, so first of all, what is 2 of n? 2 of n factorial means the order matters, right? Go from P1 to P2 to P3 was if you go from P2 to P1, and this order matters. 2 of n means I want to just select which one, right? Out of all the 18s, I want to select first one, second one. So it means I just want to know what are they. The order does not matter. How do I convert a problem that is order matters to order does not matter? This is what we're trying to solve here. Okay, so let's look at A of vector P first. Okay, so it's sigma I from 1 to k m of I. Right? So it does not matter which order you take. The sum of mi is the same. So that is sine of, let me use P to represent this. Okay, the set, the collection of P1 to Pn, regardless of order. So for the first one, A of vector P, the order does not matter. Okay, the second one, B of vector P, Okay, so that equals, if I copy from above, sorry, sigma I from 1 to u of m of I times sigma j from I to u minus 1 distance of from p of j to p of j plus 1. The order actually for this one matters, right? So what happens is, so what happens is when you, let's say first one is this, right? I mean, the last one is you. You can go from here to here, right? So from here, you of m of k minus 1 times this distance. Then if you go to this one, it's m k minus 2 times this distance plus this distance, okay? So however, remember, we in the convex hull, right? We just want to find the hull, right? So we just want to find the maximum value, remember? Remember, we just want to find this maximum value, okay? So that means we actually want to find for all the vector p's, what is the max of b of this p? I mean, actually, in this case, it's a minimum because you want to find the smallest one, right? So let's say you have two of them with the same slope. You want to find the one which is the smallest because it's negative, right? So we want to find the minimum, okay? So if we can find the minimum for all the p's, for that make this set, right? Make this set, okay? If we can find that value, then I can convert it to be, so then maximum of b for vector p for its b of, let's call it as this, b optimum for that set, right? For this set, okay? Now, question is, how do we do that? Let's look at it here. If I have something that is reached a point u, okay? If I want to go to next point, if I find the, let's say I have bunch of points, right? P1, P2, P3, whatever, all the way to u. There's many different ways I can go from here to there, right? With this vectors, I can have different vectors. But within this set, let's say I already find the optimum of this. Let's say now I have a new set, new one, which is V. How can I find the optimum of that? Okay, let's define another dp. Let's say dp2. It's, I already reached the u, and the remaining set, that's I have not reached. Let's call that set is q. So basically, q is the full set. It's complementary of p, right? Basically, is the point, the full set, the n sets minus the p set, right? When I say minus, I mean logically minus, right? So for example, the additional points, that is, let's say this is pk plus 1, pk plus 2, the remaining set that is not in the one I already visited. So then which is Q is where I'm going to visit, right? So then if I go from U to V, okay, so dp2 of V has a different Q, right? Let's call it Q prime. So obviously Q prime is Q minus V, right? Again, this minus, I mean, remove V from this Q set, right? Because V originally is in this Q set, I remove that. So this is what? This is you take all the things, you take all the points, right, which is in this set. What is this set? This is the opposite of Q, right? Like Q is this opposite of Q. You take all those points from here, from this set, right? X belong to that. Sorry, this is Q, right? X was X come from this opposite of Q set, right? Then let's say this is your X, right? You go from here to V, right? Plus distance from X to V, right? So that is your transformation, right? If you have this, then you can calculate each of that. Right? Then if you get that, then obviously, this is what I mean for this P of P optimum, right? P of P optimum. Okay, so you can calculate the backwards. Basically, you can calculate the backwards. You can use this dp. You can get what is the b, right? So this can be calculated ahead of time, right? So once you calculate this ahead of time, then you simplify this problem. You simplify the problem here, right? You simplify this problem to original problem dp of this p, not vector p anymore. It's the only this set, right? And that u is a, which is only depends on the set, minus b optimal, which is also only depend on the set, not the vector. Okay, this is calculated from dp2, right? So dp2 of go to u, and this q is complementary of p, right? So now you only depends on p now, not the vector of p. So that is 2 to the power of n. Right? So that's how you convert this problem. Okay? So two algorithms I used here. One is I used the traditional convex Hall trick, right? That's pretty a standard one now. We have used this trick, I record at least 2 or 3 times in the previous Platinum level problems. I think like at least like 5 years ago, we already used this, right? So this is a pretty standard trick. If you have linear equation and you want to find the maximum or minimum, right? Then the tricky thing is, how do I convert from n factorial complexity to 2 to the power of n? So I have to recognize something that is not dependent on the order of of the set, right? So A does not depend. B, I have to make another DP to make it to find the optimum point so that does not depend on it. Okay. So that's pretty much this problem. So this week's homework is obviously take this and code it up. Right? And then next week, we're going to talk about the third problem, which is subtree activation. Right. So have a good weekend. Thanks, everybody.